For a while now, scientists have gone back to seriously pondering if we're alone in the universe. This is due to the thousands of messages they've been getting from space from a single huge and mysterious source. What is sending these messages? Can we ever decode these messages? What is anyone out there trying to tell us? In this video, we dive into the details of how scientists have just detected something huge in space that keeps sending us thousands of messages. For many people, fast audio burst means nothing. However, to astronomers, scientists, and avid space lovers, fast radio burst, or FRB, is one of the latest fascinations. Part of its allure is its mysteriousness, as not everything about it has been discovered. And when scientists began to pick up numerous FRB signals within a short period of time, the excitement couldn't be contained, and the signals won't stop. Space is full of deep mysteries that may take us forever to unravel, and FRB is one of them. And receiving these FRB signals is suggesting that somebody wants our attention, should we answer the call. But what exactly is FRB? FRBs are intense bursts of radio emission that last milliseconds. They exhibit the characteristic dispersion sweep of radio pulsars. The first FRB was discovered and documented in 2007 by Lorimer and Co. However, pursuing archived data, scientists realized that FRB were actually observed about 6 years earlier in a pulsar survey of the Magellanic Clouds. Because one of the people that discovered it was named Lorimer, FRB is also known as the Lorimer burst. When a telescope captures an FRB, one of the most important features researchers look at is something called dispersion. Dispersion is basically a measure of how stretched out an FRB is when it reaches Earth. The plasma that is found between stars and galaxies causes all light, radio waves included, to slow down. However, lower frequencies feel this effect more strongly and slow down more than higher frequencies. FRBs contain a series of frequencies. The higher frequency light in the burst gets to the Earth before the lower frequencies causing the dispersion. Researchers try to use this dispersion to estimate how far from Earth an FRB originated. The principle is that the more stretched out an FRB is, the more plasma the signal must have passed through and the farther away the source must be. So let's quickly tell you what the first FRB looked like. It was like giant pulses from radio pulsars like the Crab with extreme intensity and observed across a 288 MHz radio band. It was traced to near the location of the small Magellanic Cloud. Meanwhile, the scientists could not measure the flux exactly because of the limited dynamic range of the instrumentation, but the first FRB has been estimated to be able to occur in several 100 bursts every day with a small probability of detection. Now, for many years after the first FRB, it was thought to be unique, and one of the convincing pieces of evidence of its existence was that it occurred in 3 of the 13 beams of the park's multi-beam receiver. Some years later, a Swinburne student named Sarah Burke-Spoleyor published some disturbing findings that she got from reanalyzing 2 other pulsar surveys. She was hunting for other bursts and ended up with the discovery that at almost the exact dispersion of the Lorimer burst, there were other swept sources of radio emission, but that they occurred in all beams. At this point, interest in FRBs had started to wane. However, fast forward to 2013, and a dramatic thing happened in the subfield of FRBs. Thornton and Co. detected another 4 Lorimer bursts. This was when they were officially named fast radio bursts, or FRBs. The FRBs discovered by Thornton and Co. had dispersion measures that were significantly higher than the original Lorimer burst. These 4 bursts were found as part of the high time resolution universe surveys conducted at the park's 64-meter radio telescope. The brightest of the bunch displayed a classic dispersion sweep and showed scatter broadening with power law dependencies exactly like we'd expect from true extraterrestrial sources of radio emission. Meanwhile, the first FRB discovered in another observatory was announced in 2014. It was recorded at Arecibo and was traced to the direction of the galactic anti-center. However, they have remained controversial in their source, and that is exactly what scientists are trying to figure out because it's just baffling. The mysteries deepened when scientists analyzed a set of data obtained in 2019. The analysis took place in 2021 and revealed 1,652 flares were produced in a period of just 47 days. The flares were from the FRB 121102 source. It set the record for the number of flares discovered from any FRB, but it also opened up a new perspective to researchers about FRBs, investigating or searching for periodicity or regular time spans between similar bursts. However, the scientists were disappointed because they couldn't find any sign of periodicity. They complained that the lack of periodicity posed a problem. It made it challenging to pinpoint the source, to nail it down to a spinning compact object, for example, from a highly magnetic dead star or magnetar. But it was enough for the scientists to suggest that these FRBs could be produced from more than one mechanism. They also had to accept it might be a long while before we understand FRBs or even decode them if they represent secret messages. The lack of periodicity aside, most FRB sources flare once, and that is all. Scientists don't hear from them again. This has been another challenge when predicting or trying to trace them. However, a handful of the FRBs have been giving off signals repeatedly. One of the most prolific is FRB 121102. Its repetition has allowed scientists to trace it to a dwarf galaxy 3 billion light-years away. But of course, it's a real weirdo. It is extremely active and follows a pattern. It has a 90-day period of activity followed by 67 days of silence. The level of activity of FRB 121102 has given astronomers the chance to catch it when emitting. One of the instruments that have helped detect this particular FRB is the 500-meter Aperture Spherical Radio Telescope, or FAST. The telescope started picking up FRBs even during its commissioning stage. In just 2 months, FAST gathered the data mentioned earlier in a 47-day period over a cumulative total of 59.5 hours. The peak rate was 122 bursts over the course of 1 hour, or the highest level of activity we've ever seen in a fast radio burst source. This massive haul of detections allowed for statistical analysis of the source's activity. The researchers categorized the bursts into 2 different kinds, with higher energy and lower energy bursts displaying distinctly different properties. The weaker ones turned out to be more random in nature. However, the lack of periodicity from most other FRBs has not stopped scientists from trying to trace them. Those they could trace were found to originate from galaxies that are millions and even billions of light-years away. But even though they are so far away, they produce bursts so powerful that within a few milliseconds, they can discharge the energy equivalent to hundreds of millions of our Sun. More recently, scientists discovered another FRB which was named FRB 190520 using the same FAST telescope in China. One of the interesting features of this FRB is that it's one of the few repeating bursts. It also repeats itself more frequently than the others. It produces 75 bursts in just 6 months. The team then used the Very Large Array radio telescope located in New Mexico to study the FRB more. They were able to successfully pinpoint the location of its source. It came from a dwarf galaxy roughly 3 billion light-years from Earth. One of the things the team discovered was that there was a persistent, though much fainter, radio signal being emitted by something from the same place that FRB 190520 came from. Of the more than 800 FRBs that have been discovered to date, only one other has a similar persistent radio signal. Since the team could determine that the FRB came from a dwarf galaxy, they could determine just how far away that galaxy is from Earth. But that was where the results stopped making sense. To their surprise, their distance estimate based on the dispersion of the FRB was 30 billion light-years from Earth, which is actually about 10 times larger than the actual 3 billion light-years to the galaxy. That is both usual and unusual. Out of the 800 FRB sources, only 19 have been traced to their origins. This means the distance from Earth can be ascertained for those 19. But for the remaining FRBs, astronomers have to rely on dispersion alone to estimate their distance from Earth. For the other 19 FRBs with known locations, the distance is estimated from the dispersion, very similar to the real distances to their source galaxies. But this new FRB is different because the estimates made by the dispersion method were incorrect and threw many assumptions out the window. And the discovery of FRB 190520 raised even more questions which have still not been answered. For instance, are persistent radio signals becoming more common? What conditions produce them? Is the same phenomenon that produces FRBs responsible for emitting the persistent radio signal? Another thing that baffled scientists about FRB 190520 is that the dispersion is greater than it should be. What could have caused it? Is the cause something near the FRB? Is the cause associated with the FRB itself? The team that discovered FRB 190520 has committed to continue studying it using a host of different telescopes around the world. Perhaps the discovery of more FRBs in the future will allow scientists to understand them very well. Let's hear what you think of FRBs in the comments section below.